Tonight, we're going to ask the one question that physics is not supposed to answer. Not because it's too dangerous, not because it's forbidden, but because the tools we normally use to answer questions about the universe stop working before we can even get close to it. The question is this: what existed before the Big Bang? You've probably heard that this question is meaningless. That asking what came before the Big Bang is like asking what's south of the South Pole. That time itself began at the Big Bang, so there was no before. That the question contains a false assumption, the assumption that there was a before at all. You've heard that, and the people who told you that are some of the most brilliant physicists who ever lived. They're not wrong, exactly. But they're not entirely right either, because in the last 30 years, something strange has happened in physics. Theorists who started from the assumption that the question was meaningless ended up, almost against their will, producing answers. Not definitive answers, not answers everyone agrees on, but genuine, mathematically coherent proposals for what might have existed before the universe we live in, for what might have caused the Big Bang, for what the bang was actually banging into and what it came from. And what they found is stranger than you can imagine. Before we go any further, if this kind of deep exploration is the sort of thing you find yourself thinking about at midnight, a quick like or subscribe really does help this channel keep going. It means more of this. Now let's begin. Let's start with what you think you know about the Big Bang. Most people carry around a picture in their heads, a picture that was probably shaped by a documentary they watched at some point or a textbook illustration. The picture looks something like this: nothing, and then suddenly an explosion, a point, a hot, dense point appearing from nowhere, expanding outward into space, cooling as it goes, eventually producing all the galaxies and stars and planets in you. This picture is wrong in almost every detail, and the ways it's wrong are important because they're what lead us toward the real question, the one that can't be dismissed. Let's fix the picture. First, the Big Bang was not an explosion into pre-existing space. Space itself was part of what expanded. There was no surrounding, empty void into which the early universe expanded. The expansion was of space itself. The matter and energy that would eventually form everything you see in the night sky was not moving through space. The space between it was growing. Imagine dots drawn on a balloon. Now inflate the balloon. The dots aren't moving across the surface of the balloon. The surface itself is stretching. Every dot sees every other dot moving away from it, not because the dots are moving through the rubber, but because the rubber between them is expanding. That's closer to the real picture. Second, the Big Bang wasn't really an explosion in the colloquial sense. There was no shockwave, no outward blast from a central point. Every point in space was equally the center of expansion. If you were a photon created in the first second of the universe, you would have observed the exact same expansion in every direction. There is no special place in the universe that was the origin point. Every place was the origin point. Third, and most importantly, the Big Bang is not a description of the first moment. It is a description of the earliest moment we can describe mathematically, which is a very different thing. This is the point where the picture really breaks down and where the real question begins. Our best theory of the universe's early history is a combination of general relativity, Einstein's theory of gravity, and quantum mechanics, the theory governing the behavior of subatomic particles. When we run these theories backward in time, we can describe the universe with increasing confidence as we approach the first moments. We can describe what the universe was like 1 second after the Big Bang. We can describe what it was like 1/1,000,000,000 of a second after the Big Bang. We can describe with somewhat less confidence what it was like at even earlier times. But at a certain point, the math breaks down, completely and irreparably. That point is called the Planck time. It's approximately 10 to the power of -43 seconds. Written out, it looks like this: 0.1 seconds. 1/10 of a millionth of a trillionth of a trillionth of a trillionth of a second after the beginning. Before the Planck time, our equations produce nonsense, not approximately wrong answers, not answers we're uncertain about, mathematical nonsense, infinities where there shouldn't be infinities, division by zero, outputs that have no physical meaning. This isn't a failure of our computers or our mathematical technique. It's a fundamental incompatibility between the two best theories in physics. General relativity, the theory that governs the large, and quantum mechanics, the theory that governs the small. In normal circumstances, these two theories occupy different domains and never have to talk to each other. But at the Planck scale, at the densities and energies that existed at the very beginning of time, both theories are simultaneously necessary. And when you force them to work together, they produce contradictions. This means that everything we know about physics, every tool we have for understanding the universe, becomes useless before a certain moment. We have a hard wall at the beginning of time. And beyond that wall, we genuinely do not know what the laws of physics are. So when someone asks what came before the Big Bang, the technically precise answer is, we have no working theory that can tell us. Our current tools hit a wall exactly where the answer would be. But here's what makes this so fascinating. Having no current theory isn't the same as having no answer. It just means the answer requires new physics. And new physics is exactly what theorists have been trying to build. Over the last several decades, a number of serious, mathematically sophisticated proposals have been made. Each one takes a different approach to the wall at the beginning of time. Each one produces a different picture of what might lie beyond it. Each one is genuinely strange. And understanding why they're strange requires understanding something about the nature of time itself. Because the real answer to what came before the Big Bang might not involve anything coming before it at all. It might require that the question itself be replaced by a different, deeper question. Let's go back to the beginning. Not the beginning of the universe, but the beginning of our understanding of it. The story of how we discovered the Big Bang is one of the great detective stories in science. And like most detective stories, it begins with someone noticing something that wasn't supposed to be there. In 1929, an astronomer named Edwin Hubble made a discovery that would change our picture of the universe forever. He was measuring the light coming from distant galaxies, and he noticed something systematic in that light. Almost every galaxy he looked at had its light shifted toward the red end of the spectrum. Redshifted. And the farther away the galaxy was, the more redshifted its light was. You've probably encountered the concept of redshift before, but let's make sure the picture is clear. When a source of sound is moving away from you, the sound waves get stretched out. The wavelength gets longer. The pitch drops. This is why the engine of a race car sounds different as it approaches you versus as it moves away. The sound as it approaches is higher pitched. The sound as it recedes is lower pitched. This is the Doppler effect. Light behaves the same way. When a source of light is moving away from you, the light waves get stretched. A longer wavelength in visible light corresponds to a shift toward the red end of the spectrum. A source moving toward you would be blue shifted. What Hubble was seeing then was that almost every galaxy was moving away from us. not just a few, almost all of them, in every direction. The natural interpretation of this is disturbing. We're at the center of some vast outward explosion, and everything is fleeing from us. We're special. We're the origin point, but we're not. Here's the critical insight. Imagine our balloon again, with dots on the surface. Every single dot sees every other dot moving away from it as the balloon inflates. There is no special dot. Every dot is equally the center of expansion from its own perspective. This is exactly what Hubble was seeing. He wasn't seeing everything fleeing from Earth. He was seeing space itself expanding. The space between galaxies was growing, and the light traveling across that growing space was being stretched as it traveled, which is why it arrived redshifted. The implication is staggering. If everything is expanding away from everything else now, then in the past everything was closer together. And if you run the expansion backward far enough, everything converges. All the matter and energy in the observable universe was once compressed into an extraordinarily small, extraordinarily hot, extraordinarily dense state. This is the Big Bang, not an explosion in space, an explosion of space, or more precisely, the beginning of an expansion of space that continues to this day. Georges Lemaitre, a Belgian priest and physicist, was actually the first to propose this idea formally in 1927, 2 years before Hubble's announcement. He called it the hypothesis of the primeval atom, the idea that the universe began as a single quantum, a single point of infinite density from which everything emerged. The name Big Bang itself was coined by Fred Hoyle, a British astronomer who actually didn't believe in the theory. He invented the name as a way of mocking it on a BBC radio program in 1949, but the name stuck and the mockery didn't. Confirmation of the theory came in 1965 when two physicists working for Bell Labs, Arno Penzias and Robert Wilson, were trying to figure out why their radio antenna was picking up persistent background noise they couldn't eliminate. The noise was the same in every direction. It had the spectrum of a blackbody at a temperature of about 27 degrees above absolute zero. It was coming from everywhere in the sky simultaneously. What they had stumbled on was the cosmic microwave background radiation, the afterglow of the Big Bang itself. Here's what that means. In the very early universe, everything was so hot and dense that matter and light were coupled together in a seething plasma. Photons couldn't travel freely. They were constantly being absorbed and re-emitted by the hot, dense plasma. The universe was opaque, but as the universe expanded and cooled, eventually the temperature dropped to the point where electrons could combine with protons to form neutral hydrogen atoms. This happened about 380,000 years after the Big Bang. When it happened, the universe became transparent almost instantly. The photons that had been trapped in the plasma were suddenly free to travel, and they've been traveling ever since, for 13.8 billion years, in every direction, filling all of space. That's what Penzias and Wilson detected. The light from 380,000 years after the Big Bang, stretched by the expansion of the universe into microwave wavelengths, arriving at their antenna from every direction equally. It was the oldest light in the universe. It was the echo of the beginning. The cosmic microwave background has since been mapped with extraordinary precision by satellites including COBE, WMAP, and most recently Planck. The temperature variations across the sky are tiny, about 1 part in 100,000, but they're real. And those tiny temperature variations encode information about the earliest moments of the universe, about the seeds that would grow into the galaxies and galaxy clusters we see today. The Big Bang is not a hypothesis. It is one of the best supported theories in the history of science. The evidence for it is overwhelming, consistent, and comes from multiple independent lines of observation. But confirming that the Big Bang happened is not the same as understanding what happened at the Big Bang, and it certainly doesn't answer what came before. The mathematical description of the Big Bang tells us that as we go earlier and earlier in time, the universe was hotter and denser. The temperature and density increase without limit as we approach the beginning. In the standard mathematical description, at time equals 0, both the temperature and the density are infinite. Physicists call this a singularity. A singularity is not just a very large number. It's a place where the mathematics breaks down completely. Where the output of the equations is not a very large finite number, but is actually infinite, which has no physical meaning. A singularity in physics is like a divide by zero in arithmetic. It doesn't give you an answer. It tells you the question has been asked in the wrong way. When the equations produce a singularity, it usually means one of two things. Either something genuinely extraordinary is happening at that point, something the equations aren't equipped to describe, or the equations themselves are wrong, approximations that break down at extremes. In the case of the Big Bang singularity, most physicists believe it's the second option. Our equations work beautifully for the universe as it is today, and as it was in its early but not earliest history. But they're known to be incomplete. They can't account for quantum gravitational effects, and at the Planck scale, quantum gravity is not a small correction. It's the dominant physics. The singularity is almost certainly a mathematical artifact of using equations in a regime where they don't apply, not a description of a physical moment where density and temperature were literally infinite. This means the real story of the beginning is hidden behind a mathematical wall. We need new physics to see through it, and new physics is exactly what theorists have been building. Let's look at what they've found. Before we can talk about what came before the Big Bang, we need to talk about something that feels even more fundamental. We need to talk about time itself. Because the most honest answer to the question of what came before the Big Bang is not a description of some prior state of the universe. It's a challenge to the word before. Here is a thought that might unsettle you more than almost anything else we discussed tonight. Time might not be a fundamental feature of reality. It might be something that emerges from something deeper. And if that's true, then asking what came before the Big Bang might be like asking what's colder than absolute zero. Not a question with an answer, a question that contains a logical impossibility. To understand this, we need to understand how time actually works, not in the intuitive everyday sense, but in the way that physics describes it. In everyday life, time feels like a river. It flows. It has direction. Things happen in sequence. Cause precedes effect. The past is fixed and the future is open. The present moment slides continuously forward like a bead moving along a string. This intuition is wrong, not in small ways, in deep, fundamental ways that physics has understood for over a century, but that most people never internalize. The first blow to intuitive time came from Einstein. In 1905, with his theory of special relativity, Einstein showed that time is not absolute. It does not flow at the same rate for everyone. A clock on a fast-moving spaceship runs slower than a clock sitting still, not because the clock is broken, not because of some mechanical effect of motion, but because time itself passes more slowly for moving objects. This has been measured directly. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground. The difference is tiny at airplane speeds, but it's real, measurable, and predicted exactly by relativity. The second blow to intuitive time was deeper, also from Einstein, but from his 1915 theory of general relativity. This theory showed that time is not just relative, it's geometric. Spacetime, the unified fabric of space and time, has geometry. It curves in the presence of mass and energy, and what we experience as gravity is the effect of objects following the curves of this geometry. A heavy object like the sun doesn't pull on the Earth through some invisible force acting across empty space. The sun warps the geometry of spacetime around it, and the Earth follows the straightest possible path through that curved geometry, which happens to be in orbit. This means time is not a container that physics happens inside. Time is part of the physics. It's a dimension of spacetime, subject to the same equations as space, capable of curving and stretching. And here's where it gets relevant to our question. In the Big Bang, according to general relativity, it's not just matter and energy that were compressed into a dense early state. Spacetime itself was compressed. The geometry of time was part of what was evolving. And if time itself is a physical entity that emerged with the universe, then the question of what came before it starts to look very different. A mathematician named Stephen Hawking, working with James Hartle in the 1980s, pushed this idea as far as it could go. They proposed something called the no-boundary proposal, and it's one of the most conceptually strange ideas in all of physics. Here's the core of it. In classical general relativity, if you run the universe backward in time, you hit a singularity, a beginning, a moment before which there is nothing because time itself begins there, the boundary of time, a hard edge. But Hawking and Hartle argued that if you incorporate quantum mechanics into the description of the very early universe, something strange happens to time. It becomes, in a precise mathematical sense, more like space. To understand what this means, you have to understand a mathematical technique called imaginary time. Not imaginary in the everyday sense. Imaginary in the mathematical sense, meaning time multiplied by the square root of -1. This sounds like pure abstraction, and it is, but it has a profound physical interpretation. When you replace ordinary time with imaginary time in the equations of the early universe, the equations change in a very specific way. The distinction between the time dimension and the space dimensions disappears. Spacetime becomes a purely spatial geometry, four-dimensional space, with no special dimension that functions as time, no arrow of time, no past or future. In this picture, the early universe doesn't have a beginning in time. It has a boundary, but that boundary is like the South Pole. There's nothing south of the South Pole. Not because there's a wall there, not because you hit an obstacle, but because the direction south simply ceases to exist there. You run out of south. Space ends. Similarly, in the Hartle-Hawking no-boundary proposal, as you go back toward the beginning of the universe, the time dimension smoothly changes into a spatial dimension. There's no point at which time begins. There's simply no more time as you move in that direction. Time ends the way south ends at the South Pole. What this means for the question of what came before the Big Bang is profound. There was no before, not in the sense that there was a before and it was empty. Not in the sense that the universe existed and nothing happened yet, but in the sense that the concept of before simply doesn't apply at that boundary. The universe in this picture has no cause in the ordinary sense. It doesn't pop out of some prior state of the universe. It doesn't emerge from a pre-existing void. The question of what caused the Big Bang in this picture is exactly like the question of what's south of the South Pole. Not unanswerable, inapplicable. Now, the no-boundary proposal is beautiful and conceptually elegant, but it is deeply controversial, and not everyone accepts it. There are serious technical objections, questions about whether imaginary time is physically meaningful or just a mathematical trick, questions about the probability measure on the space of possible universes it generates, questions about whether it actually predicts the universe we observe. But the conceptual point stands, regardless of whether the Hartle-Hawking proposal is correct in its details. Physics has identified a genuine possibility in which the question of what came before the Big Bang is not a question with an answer, because the concept of before doesn't apply at the boundary of time. This is unsatisfying for some people. It feels like a dodge, like the physicist is saying we don't know, so we'll claim the question is meaningless, but it's not that. It's something more interesting. It's a mathematical demonstration that the structure of spacetime at the earliest moments might genuinely not have a before. That time as a concept might have a geometric boundary, the way that south as a direction has a geographic boundary. And if you understand that boundary geometrically, the question dissolves not because we're dodging it, but because we've understood it more deeply. Still, many physicists are not satisfied with this answer. They want to know what's on the other side. They want a story, and they've been building one. Let's talk about what that story might look like. There is a moment in theoretical physics when a problem becomes so deep that the community fragments. When different groups of brilliant people, all working from the same data, all using the same tools, arrive at different answers because the problem itself requires assumptions that the data can't yet adjudicate. That's the situation with the origin of the universe. Right now, there is no consensus. There is no accepted theory of what came before the Big Bang, or what caused it, or whether those questions even make sense. What there is instead is a landscape of proposals. A set of competing ideas, each of which is mathematically coherent, each of which is genuinely strange, and none of which has been confirmed by observation. But they're not wild speculation. These are serious, peer-reviewed, mathematically sophisticated proposals developed by some of the best physicists in the world. They make different predictions. Some of those predictions might, in principle, be testable. And understanding them, even at a conceptual level, opens up a kind of vertigo that nothing else in science can match. Let's walk through them. The first proposal we need to understand is cosmic inflation. And while inflation is often presented as part of the standard cosmological story, it actually contains within it some profound implications for the question of what came before. Inflation was proposed in 1980 by Alan Guth, a physicist at MIT. He was trying to solve a set of problems with the standard Big Bang model that had been bothering cosmologists for years. The first problem is called the flatness problem. The universe, as we observe it, is extraordinarily flat. In the geometric sense of spacetime, the curvature of the universe is very close to zero. In fact, observations suggest it's so close to zero that it's effectively zero. But in the standard Big Bang model, this flatness requires extraordinary fine-tuning of the initial conditions. The universe at the Planck time would have had to be flat to 1 part in 10 to the 60th to produce the flatness we observe today. That's a 1 followed by 60 zeros. There's no physical reason why the initial conditions would be that precisely tuned. The second problem is the horizon problem. The cosmic microwave background is the same temperature in every direction to 1 part in 100,000. This means that regions of the universe that, according to standard Big Bang cosmology, were never in causal contact with each other, regions so far apart that light could never have traveled between them before the CMB was emitted, somehow have the same temperature. They couldn't have come to equilibrium by exchanging energy. They never had contact. And yet they're the same. Guth's proposal was brilliant in its simplicity. He suggested that in the very early universe, before about 10 to the power of -32 seconds, the universe underwent a period of exponential expansion. An expansion so fast that every region of space doubled in size every tiny fraction of a second. The universe expanded by a factor of at least 10 to the 26th in an incredibly brief period. Think about what this does. If the universe was once tiny and connected, small enough that all its regions could exchange energy and reach thermal equilibrium, and then that tiny connected region expanded by a factor of 10 to the 26th, what you end up with is a vast universe in which every region was once in contact. The horizon problem dissolves. And the flatness problem dissolves too, because any initial curvature gets diluted to essentially zero by the enormous expansion. The same way any small patch of a balloon's surface looks flat if the balloon is inflated to enormous size. But inflation creates a new mystery. What caused it? Guth proposed that the universe was briefly stuck in a particular quantum state, a state of very high energy that is inherently unstable. This state generates a kind of anti-gravity, a negative pressure that causes the exponential expansion. Eventually, the field driving inflation, called the inflaton field, decays into ordinary matter and energy, ending inflation and producing the hot, dense state that we call the Big Bang. The transition between the inflationary state and the hot Big Bang is called reheating. Now here's where things get relevant to our question. If inflation happened, what was happening before inflation? What was the inflaton field doing before it drove this period of exponential expansion? Was there a universe before inflation? One of the most striking implications of inflation comes from work done in the 1980s by Andre Lind, one of Guth's collaborators and competitors. Lind realized that in most inflationary models, inflation doesn't just happen once. It happens everywhere, always, eternally. Here's why. In the quantum mechanical picture of the inflaton field, different regions of space have slightly different field values due to random quantum fluctuations. In some regions, the field fluctuates toward a value that drives more inflation. In those regions, the exponential expansion continues. In other regions, the field decays and inflation ends, producing a hot Big Bang and eventually stars and galaxies and beings who wonder about the beginning. But here's the key. The regions that keep inflating expand so fast that they always outnumber the regions where inflation ends. Inflation, once started, reproduces itself faster than it ends. Somewhere out beyond the reach of any telescope, inflation is still going on. It has been going on since before our Big Bang and will continue long after. Our universe, our observable bubble of space, is one of an enormous or possibly infinite number of bubble universes that have nucleated out of this eternally inflating background. This is called eternal inflation, and the collection of bubble universes it produces is called the multiverse. The multiverse is not science fiction. It is a genuine prediction of eternal inflation, which itself is a genuine prediction of the inflationary models that best fit our cosmological data. Most cosmologists who work on inflation believe eternal inflation is a real consequence of the physics. But eternal inflation also changes the question of what came before. If the universe is embedded in a larger eternally inflating background, then our Big Bang didn't come from nothing. It came from a quantum fluctuation in an inflating background. There was something before. It's just not a universe in the ordinary sense. It's the eternally inflating pre-cosmic soup from which all bubble universes nucleate. But then what came before that? And here the honest answer is, we don't know. The eternally inflating background might itself have a beginning, or it might have always existed in some form, or time might not apply to it in the way we're imagining. We've pushed the question back, but we haven't answered it. Other proposals try harder to actually answer it. The cyclic model, developed by Paul Steinhardt of Princeton and Neil Turok, takes a completely different approach. In their proposal, the Big Bang was not a beginning, it was a transition, a moment when a universe that had been contracting underwent a bounce and began expanding again. The universe oscillates. It expands, slows, perhaps contracts, bounces, expands again. What we call the Big Bang is not the beginning of everything. It's the most recent bounce in a cycle that may have been going on forever. The cyclic model doesn't require a beginning. There is no before in the sense that there is no first cycle. The cycles extend backward indefinitely. Time exists before our Big Bang. It's just a different phase of the universe's evolution. The original versions of the cyclic model had serious problems. Each bounce would increase the entropy of the universe, and a universe that had been cycling forever would have infinite entropy, which is physically absurd. More recent versions, developed in the context of string theory, try to avoid this problem by proposing that each cycle genuinely resets the entropy of the universe. But these models are still being developed and haven't achieved consensus acceptance. There's also a set of proposals that emerge from loop quantum cosmology, a specific approach to quantum gravity that we'll discuss in more detail later. In loop quantum cosmology, the singularity at the beginning of time is replaced by a bounce. The quantum geometry of spacetime doesn't allow infinite density. When the density reaches a maximum value set by the Planck density, the gravitational force becomes repulsive rather than attractive, and the contraction reverses. Our expanding universe was preceded by a contracting universe. In loop quantum cosmology, there was a before. It was another universe, collapsing toward the conditions that produced our Big Bang. And then there is the most exotic proposal of all, the idea that the universe was created from nothing. Not from a quantum vacuum, which is something. Not from pre-existing spacetime or inflating background or prior universe. From literally nothing. This is the proposal of Alexander Vilenkin, a physicist at Tufts University, and understanding it requires going deeper into the quantum nature of reality. Nothing is not empty. This is one of the strangest things that quantum mechanics has taught us, and it is directly relevant to the question of what came before the universe. To understand how a universe might emerge from nothing, you have to understand why quantum mechanics makes nothing impossible. In classical physics, empty space is really empty. If you remove all the matter from a region of space, remove all the light and all the fields and all the particles, you get a void. Absolute nothingness. Zero energy. Zero activity. Nothing. But quantum mechanics doesn't allow this. And it doesn't allow it for a reason buried deep in its mathematical foundation. The Heisenberg uncertainty principle tells us that there is a fundamental limit to how precisely we can know certain pairs of physical quantities simultaneously. The most famous example is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving. These aren't limitations of our measurement technology. They're not due to the disturbance of measurement. They're a fundamental feature of reality. Position and momentum are not simultaneously well-defined. A similar uncertainty relation holds between energy and time. The more precisely you define the time interval over which a system's energy is measured, the less precisely the energy itself can be known. This means that in any tiny interval of time, the energy of any region of space is uncertain. It fluctuates. It cannot be exactly zero. This means empty space is not empty. It is alive with fluctuations. Virtual particles are constantly appearing in pairs, existing briefly and annihilating. Fields fluctuate around their average values. The energy of the vacuum is not zero. It has a minimum energy, called the zero-point energy, that cannot be removed. This is not theoretical speculation. It is directly measurable. The Casimir effect is a direct consequence of vacuum fluctuations. If you place two uncharged metal plates very close together in a vacuum, they attract each other. The reason is that the metal plates restrict the wavelengths of the virtual photons that can exist between them, while outside the plates all wavelengths are possible. This creates a pressure difference and the plates are pushed together. This effect has been measured precisely in multiple experiments. The vacuum is real. Vacuum energy is real. Now, if the quantum vacuum is not truly empty, if it is a roiling sea of fluctuations and virtual particles, then the question of creation from nothing becomes more subtle. Alexander Vilenkin's proposal works like this. In quantum mechanics, a process that is energetically forbidden in classical physics can nonetheless occur with a certain probability. Particles can tunnel through energy barriers that classically they could never surmount. This quantum tunneling is well established. It underlies the mechanism of radioactive alpha decay. It's the basis of the tunnel diode. It is real. Vilenkin proposed that the universe itself might have tunneled into existence, not from a prior universe, not from an inflating background, but from a state of zero size, from nothing. Here is what he means, as precisely as I can convey it without the mathematics. In quantum gravity, there is a description of a universe as a quantum mechanical wave function. Just as a particle has a wave function that describes the probability of finding it at different positions, a universe has a wave function that describes the probability of finding it with different sizes and geometries. This wave function obeys equations derived from combining quantum mechanics and general relativity. Vilenkin's insight was that the wave function of the universe allows for a non-zero probability of finding the universe with a very small but non-zero size, even when starting from a state of zero size. The universe can tunnel from nothing to something, from zero radius to a small but finite radius. And once it exists with that small radius, if the conditions are right, inflation can take over and drive it to the enormous size we observe. The key word is nothing. Vilenkin is careful about what he means. He doesn't mean a vacuum, which is a specific physical state. He means a state with no space, no time, no matter, no fields. A genuine mathematical zero of existence. Can quantum mechanics apply to genuine nothing? This is a deep and genuinely controversial question. Critics of Vilenkin's proposal argue that quantum mechanics itself presupposes a mathematical framework, a Hilbert space, a set of operators, a time variable. These are not nothing. They are the mathematical scaffolding within which quantum events occur. Vilenkin's nothing contains this scaffolding, even if it contains no physical stuff. It's nothing in the physical sense, but not nothing in the mathematical or logical sense. Vilenkin's response is essentially that there is no coherent concept of nothing that doesn't have some mathematical structure. That pure logical nothing, nothing with absolutely no properties, cannot even be discussed. The moment you talk about it, you've given it properties, and the minimal set of properties needed to allow quantum tunneling to occur is a coherent and minimally assumption-laden version of nothing. Whether this is satisfying depends on your philosophical commitments, but it is a genuine and carefully worked-out proposal, not a hand wave. Now there is another aspect of quantum gravity that bears on this question in a more subtle way. It concerns the nature of spacetime itself at very small scales. At the scales of everyday life, and even at the scales accessible to our most powerful particle accelerators, spacetime appears smooth and continuous. Space is the smooth, three-dimensional arena in which events happen. Time is the smooth flow along which events are ordered. But both general relativity and quantum mechanics suggest that spacetime cannot be smooth all the way down. At the Planck scale, the scale where quantum gravitational effects become important, spacetime itself is thought to fluctuate. The geometry of space and time becomes uncertain. Points in space cannot be given precise positions. Moments in time cannot be precisely ordered. Spacetime at the Planck scale is not smooth. It is foamy. This picture is called quantum foam, a term coined by John Wheeler in the 1950s. At the Planck scale, spacetime is imagined to be a seething, bubbling, fluctuating structure with topology constantly changing. Tiny black holes forming and evaporating, wormholes opening and closing. The very connectivity of space changing from moment to moment. If quantum foam is real, it has profound implications for the question of the origin. Because quantum foam is a state of spacetime that doesn't have a well-defined geometry, a well-defined time. In the foam, the concept of a single moment in time, a single well-defined present, breaks down completely. There's no unambiguous ordering of events. Time as we understand it doesn't exist in the foam. This means the boundary between the quantum foam and the classical spacetime of our universe might be the answer to what came before. Not a prior state in a prior time, but a transition from a regime where time has no meaning to a regime where time is a well-defined classical variable. The universe might have emerged from quantum foam, the way waves emerge from water. The foam is not before the wave in time. The wave emerges from the foam as a pattern that exists on a more fundamental substrate. Our universe, our spacetime, our history might be a pattern that emerged from the featureless quantum foam. This picture has been developed most systematically in the context of loop quantum gravity and in approaches to quantum cosmology based on path integrals. It is speculative. It is not yet a complete theory. But it is a genuine physical picture of how the universe might have begun without having a before. Now let's turn to a proposal that comes from a completely different direction, from string theory, and that introduces an idea so strange it will require some time to fully absorb. String theory has been described as the most ambitious theory in the history of science. It has also been described as the most overhyped theory in the history of science. Both descriptions contain truth. The ambition is genuine. String theory is the only known theoretical framework that has any hope of unifying all four fundamental forces, including gravity, into a single coherent quantum mechanical description. It has produced extraordinary mathematical insights. It has solved problems in pure mathematics that mathematicians hadn't been able to crack. It has generated a body of theoretical physics work that fills thousands of papers and has engaged the energies of many of the best mathematical physicists in the world. The critique is also genuine. After more than 50 years of development, string theory has made no predictions that have been confirmed by experiment. It is extraordinarily difficult to connect its highly abstract mathematical structure to anything measurable in a laboratory. Some critics argue that it isn't even science in the traditional sense because it makes no testable predictions. We're going to set aside most of that debate for now, because what matters for our question is what string theory says about the beginning of the universe. And what it says is genuinely strange. Let's start with the basics. In ordinary particle physics, fundamental particles are treated as point-like objects. An electron is not a tiny sphere. It's a point in space. It has no size. It occupies no volume. It is mathematically a zero-dimensional object. String theory replaces this picture. In string theory, the fundamental objects are not points but strings, tiny, one-dimensional, vibrating filaments of energy. These strings are incredibly small, about the Planck length, 10 to the power of -35 meters. They are unimaginably smaller than anything we can probe with any current or foreseeable experiment. The different particles of the Standard Model are not different objects in string theory. They are the same objects vibrating in different modes. An electron is a string vibrating in one particular pattern. A quark is a string vibrating in another. A photon is a string vibrating in yet another. All the particles of nature are harmonics on the same fundamentals. This is mathematically elegant, but string theory requires something that seemed at first deeply problematic. It requires extra dimensions of space. In ordinary physics, space has 3 dimensions: up, down, left, right, forward, backward. We can move in 3 independent directions. The mathematical consistency of string theory requires either 10 or 11 total dimensions of space and time, depending on which version of string theory you're working with. The extra dimensions are real in the theory. They are physical. They are just very small, curled up at scales below the Planck length, which is why we don't experience them. Now here's where things become relevant to the origin of the universe. In string theory, the way the extra dimensions are curled up determines the laws of physics that observers in the large 3-dimensional space would experience. Different ways of curling up the extra dimensions correspond to different values for the constants of nature: the mass of the electron, the strength of the electromagnetic force, the value of the cosmological constant. All of these depend on the geometry of the extra dimensions. When string theorists tried to count how many different geometries for the extra dimensions are possible, they discovered something stunning. The number is staggeringly large. Current estimates suggest there are roughly 10 to the power of 500 possible ways to curl up the extra dimensions. Each way corresponds to a different set of physical laws. A different universe. This collection of possible universes is called the string landscape, and it has profound implications for the question of origins. In the context of eternal inflation, the string landscape becomes the multiverse. Different bubble universes, nucleating out of the eternally inflating background, could have different compactifications of the extra dimensions. They would inhabit different points in the landscape. They would have different physical laws. Our universe is one point in this landscape. The values of the constants of nature in our universe reflect the geometry of the extra dimensions in our particular bubble. In other bubbles, those values are different. This has a disturbing implication. If there are 10 to the 500 possible universes, each with different physical laws, then the question of why our universe has the laws it does may not have a deep answer. Our laws are not the unique necessary laws of physics. They're the particular set of laws that happen to apply in our bubble. Other bubbles have other laws. This is called the anthropic principle problem, and it is deeply uncomfortable for many physicists. Because if the constants of nature are just random consequences of which bubble we happen to be in, then the project of explaining the constants from first principles is doomed. There's nothing to explain. We're in the bubble we're in. But for our question, the string landscape does provide a kind of answer to the what came before question. In the string landscape picture, our universe did not emerge from nothing. It emerged from a quantum tunneling event in an inflating background. Before our Big Bang, there was the eternally inflating background, and before that, here we run into the same problem. The eternally inflating background has to have started somehow, unless it is itself eternal. Here there is a proposal by Bauso and Polchinski and others that the landscape may be explored dynamically. That the eternally inflating background tunnels randomly between different points in the landscape over time. Our universe nucleated from one particular tunneling event. In this picture, the background has no beginning. It has always existed, tunneling through the landscape forever. But this creates a new problem. If the background has always been there, and if it has infinite past, how do we explain the arrow of time? Why is our universe in a low entropy state, with stars still burning and structure still forming? If time extends infinitely into the past, the system should have had infinite time to reach maximum entropy. And a system that has had infinite time to reach maximum entropy should be in maximum entropy. Our universe is not. This is called the Boltzmann problem, after the 19th century physicist who first formulated the problem of the arrow of time. And it is one of the deepest unsolved problems connected to the question of origins. Let's look at another proposal from string theory that takes a different approach. It's called the pre-Big Bang scenario, developed by Gabriele Veneziano, one of the founders of string theory, and Maurizio Gasparini. In this proposal, the Big Bang was not the beginning of time but a phase transition. Before our universe began expanding, it was contracting, collapsing. The strings of string theory, as the universe collapsed, behaved differently than ordinary matter. They didn't just compress. Their dynamics drove a transition that reversed the collapse into an expansion. In the pre-Big Bang scenario, the universe has existed forever. In the infinite past, it was in a state called the string perturbative vacuum, a dilute, cold, nearly empty state. It began to contract very slowly. The contraction accelerated. At some point, the density and curvature reached values where string theory effects became dominant and the classical picture broke down. And then, through mechanisms still not fully understood, the contraction transformed into expansion. Our Big Bang was that transformation. What existed before was not another universe. It was an earlier phase of our universe, contracting toward the conditions that would produce the bang. In this picture, there was a before. It was cold and empty and going in the other direction. These string theory proposals are speculative and incomplete. String theory itself, despite its mathematical richness, has not yet been formulated in a background-independent way, meaning it always assumes some pre-existing spacetime background. This makes it difficult to apply to the question of the absolute beginning, the question of how spacetime itself arose. But one approach to quantum gravity, loop quantum gravity, takes exactly this background-independent approach, and it leads to a different picture of the before. There is a path through the wall, not a way around it, not a way to dismiss it, but a specific mathematical path through the singularity at the beginning of time. It comes from loop quantum gravity, and it leads to what might be the most concrete and testable proposal for what came before the Big Bang. Loop quantum gravity is an approach to quantum gravity developed primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, beginning in the 1980s. Unlike string theory, which modifies the fundamental objects of physics, loop quantum gravity keeps the particles of the standard model unchanged and focuses entirely on quantizing gravity itself. The key insight of loop quantum gravity is this: when you apply the methods of quantum mechanics to the geometry of spacetime, you find that space cannot be infinitely divisible. Space is quantized. It is made of discrete units, the smallest possible volume being roughly the Planck volume, approximately 10 to the power of -105 cubic meters. Below this scale, the concept of volume simply does not apply. There is no smaller volume. Space is granular. The name loop quantum gravity comes from the way these discrete units of space are structured. In the mathematical formulation, the quantum states of spacetime geometry are described by networks of loops, graphs whose edges represent units of space and whose nodes represent units of volume. These networks, called spin networks, are the quantum states of geometry itself. A configuration of a spin network is a quantum configuration of space. When you apply this to cosmology, something remarkable happens. In classical general relativity, when you run the universe backward in time, the density increases without limit as you approach the singularity. The equations break down. You hit the wall. But in loop quantum cosmology, the quantum geometry introduces a correction to the classical equations. This correction is negligible at normal densities, but becomes enormous at densities near the Planck density. And crucially, this correction makes the effective gravitational force repulsive at Planck densities rather than attractive. Think about what this means. In classical gravity, matter attracts. As the universe contracts, gravity pulls everything closer, accelerating the collapse. The density increases, the gravitational force increases, the collapse accelerates further. Nothing stops it. The density goes to infinity, but in loop quantum cosmology, when the density approaches the Planck density, the effective gravitational force reverses sign. It becomes repulsive. The collapse is not just halted, it is reversed. The collapsing universe bounces. It transitions from contraction to expansion. Our expanding universe in this picture is the aftermath of a bounce. Before our Big Bang, there was a collapsing universe. It contracted to an extraordinarily high but finite density. The quantum gravitational repulsion kicked in, and the expansion we call the Big Bang began. This is called the Big Bounce, and it is not just a philosophical proposal. Loop quantum cosmology produces specific mathematical equations that govern the dynamics near the bounce. These equations can be studied. Predictions can be derived. The properties of the universe that emerged from the bounce depend on the properties of the universe that was contracting before it. One of the predictions of loop quantum cosmology is that there should be observable signatures of the bounce in the cosmic microwave background. The power spectrum of the CMB, the distribution of temperature fluctuations at different scales, might be modified in specific ways by the effects of the pre-bounce universe. These modifications are small, at the edge of what current observations can detect. But next-generation CMB experiments might be sensitive enough to find them. If signatures of a big bounce were found in the CMB, it would be the first observational evidence of a universe that existed before ours. But loop quantum cosmology also raises its own difficult questions about the before. If our universe bounced from a prior collapsing universe, what was that prior universe? Was it similar to ours? Did it have stars and galaxies and the same physical laws, or was it fundamentally different? If the prior universe contracted from an even earlier expanding phase, then we have a cycle. Universe expands, reaches maximum size, contracts, bounces, expands again. This is appealing because it avoids the question of a beginning entirely, but it runs into the entropy problem we mentioned before. Each cycle should accumulate entropy. After infinite cycles, the entropy should be infinite, and infinite entropy is physically meaningless. Some proposals for cyclic cosmology, particularly those developed by Paul Steinhardt and Neil Turok, try to avoid this problem by having the cosmological constant do work that reduces entropy during the turnaround. Whether this actually works is still debated. Others argue that the entropy problem is not as severe as it appears, that in the quantum gravitational regime near the bounce, the notion of entropy as we normally understand it might not apply, that the bounce genuinely resets the system in a way that allows cycles to repeat without entropy accumulation. We don't know. But the fact that loop quantum cosmology produces specific, mathematically well-defined equations for the bounce means there is something here to study, to derive, to compare against observation. There is one more aspect of loop quantum gravity that deserves mention in the context of our question. It concerns the nature of time itself. In classical general relativity, time is a parameter that appears in the equations. It is the dimension along which the geometry of space evolves. But in loop quantum gravity, when you write down the quantum equations governing the full system, time disappears. The equations that govern quantum spacetime in loop quantum gravity are time-independent. There is no time variable. The universe is not a system that evolves in time. It is a static quantum state, a superposition of all possible spatial geometries with no preferred time. This is called the problem of time in quantum gravity, and it's one of the deepest conceptual puzzles in physics. If the fundamental equations have no time, where does time come from? How do we recover the experience of change and evolution and sequence that is our most basic reality? The most promising answer, developed by Carlo Rovelli and others, is that time is relational. Time is not a background against which things change. Time is the change itself. In a universe with many interacting parts, the correlations between different parts constitute time. When we say that time passes, what we mean fundamentally is that one physical quantity changes with respect to another. The reading on a clock changes with respect to the positions of the stars. The oscillations of an atomic clock correlate with the growth of a tree. Time is these correlations, these relationships. In the deep quantum gravitational regime near the Planck scale, these correlations break down. There are no reliable clocks. There is no well-defined sequence. There is no time. Our experience of time in this picture is not a fundamental feature of the universe. It is something that emerged as the universe grew large and cool and complex enough to contain stable clocks and reliable correlations. Before our universe was large and cool and complex, there was no time. Not in the sense that time existed and was empty. In the sense that time, as a concept, didn't apply. This is perhaps the deepest answer to the question of what came before the Big Bang. The question assumes that time extends backward through the Big Bang, and that we can ask what was there in that prior time. But if time itself is an emergent feature of our universe, if it exists only when conditions support the kind of correlations that constitute time, then the question of what came before is genuinely unanswerable. Not because we don't have enough information, because the concept of before requires time and time didn't exist yet. But this raises a further question. If time is emergent, where did the emergent time come from? What are the timeless quantum states that give rise to it? What is the physics of that timeless regime? That's what we'll explore next. Imagine trying to describe a universe without time. Not a universe frozen at a moment in time. Not a static photograph of some instant, but a universe where the concept of moments, of sequence, of before and after simply does not apply. A universe where everything that exists without change, without evolution, without any arrow pointing from past to future. This is not science fiction. This is what the Wheeler-DeWitt equation describes. The Wheeler-DeWitt equation is the equation that results when you apply the principles of quantum mechanics to general relativity. John Wheeler and Bryce DeWitt wrote it down in the 1960s. It is the closest thing we have to a quantum equation governing the universe as a whole. And it contains no time. The wave function of the universe, according to the Wheeler-DeWitt equation, is a superposition of different three-dimensional spatial geometries. The universe is described by a quantum state that assigns amplitudes to different possible shapes of space. But there is no time variable in the equation. The state doesn't evolve. There is no history, no sequence, no dynamics. This is deeply puzzling. Our experience is that the universe changes. Stars form and die. Galaxies collide. We are born and grow old. Change and evolution are the most basic features of our experience. How do you reconcile this with an equation that says the universe is timeless? The resolution proposed by Ravelli and by Don Page and William Wouters in the 1980s is subtle and beautiful. It's called the relational interpretation of quantum mechanics, or more specifically, the Page-Wouters mechanism. Here's the idea. The universe contains many subsystems: clocks, rocks, galaxies, everything. The wave function of the universe is a superposition of different configurations of all these subsystems together. In this superposition, the state of each subsystem is correlated with the states of the others. When the clock reads 12, the sun is in a certain position. When the clock reads 6, the sun is in a different position. These correlations are part of the wave function. Now, an observer inside the universe doesn't have access to the full wave function. They can only observe subsystems. When they observe the clock, they get a specific reading. When they observe the sun, they get a specific position. And they find that these observations are correlated. The clock reading and the sun position go together in a way that traces out a sequence. From inside the universe, this sequence of correlated observations constitutes time. Time is what clocks read. The universe has time from the inside because it contains clocks and correlations between clocks and other things. But from the outside, from the perspective of the full wave function, there is no time. The wave function is static. It is a timeless mathematical object that contains within it all possible histories, all possible sequences of correlated observations, without any of them being privileged as the real present. This is strange, but it is internally consistent, and it suggests a picture of the Big Bang that is genuinely new. In this picture, the universe did not begin in time. It is a timeless mathematical structure. Our experience of time, our sense that the universe is 13.8 billion years old and expanding and cooling, is not a feature of the wave function itself. It is a feature of our position within the wave function, a feature of the particular correlations we have access to as observers inside a particular region of it. The question of what came before the Big Bang in this picture is like asking what's outside the wave function. The wave function contains all histories, all correlations, all sequences of events that constitute time. There is nothing outside it, not because there's a wall, but because outside the wave function isn't a place. Now, this is extremely abstract, and it's fair to ask whether it's genuinely physics or philosophy. Here's what makes it physics. The Wheeler-DeWitt equation makes mathematical predictions. If you can solve it, which is extremely difficult but in simplified models has been done, it gives you the quantum state of the universe. That quantum state can be analyzed to determine what observers inside it would experience. In certain simplified models, this has been done explicitly. Observers in these models do experience time, even though the wave function is timeless. The emergence of time from the timeless equation has been demonstrated mathematically in simple cases. These are not the full, realistic equations of our universe. They're toy models, but they demonstrate the principle. Time can emerge from a timeless quantum state. This connects to an even deeper question, the question of why anything exists at all. In all the proposals we've discussed, there is always something. Some prior universe, some inflating background, some quantum foam, some wave function of the universe. Even Vilenkin's creation from nothing has a mathematical structure that allows quantum tunneling. Is there any coherent picture in which there is genuinely nothing, not even the mathematical structure that allows the laws of physics to operate? This is the question of why there is something rather than nothing. And it is not a question physics has answered. Arguably, it is not a question physics can answer, because any physical answer will describe some state or structure or law, and those will be something rather than nothing. Philosopher Gottfried Leibniz asked this question in 1714. Why is there something rather than nothing? It remains unanswered. Perhaps it is unanswerable. But physics has made progress on a related question. Given that there is something, given that there is a mathematical structure of some kind, what is the minimum something that can give rise to a universe like ours? And the answer that keeps emerging from multiple directions is not much. The mathematics of quantum gravity, of inflation, of string theory, all suggest that our rich, complex, structure-filled universe can emerge from an extraordinarily simple and minimal initial state. The information content needed to specify the beginning of our universe may be much smaller than we intuitively expect. This is itself a profound result. The complexity and richness of the universe we observe, the diversity of stars and galaxies and life, may not require a complex or richly structured beginning. Simple initial conditions, evolving according to simple laws, can generate almost unlimited complexity over time. But there's something even more striking that has emerged from recent work on the information content of the universe. Something that connects the question of origins to the question of the ultimate fate of the universe. And it comes from black holes. In 1974, Stephen Hawking made a discovery that was supposed to be impossible. He showed that black holes are not black, they glow, not visibly. The glow from a stellar mass black hole is far too faint and far too cold to detect with any current instrument. But the glow is there, predicted by the most careful application of quantum mechanics to the geometry of spacetime near a black hole's event horizon. The effect is called Hawking radiation, and it is the most profound intersection of quantum mechanics and general relativity that we know of. Understanding it is essential for understanding the deeper questions about the origin and fate of the universe. Here's the mechanism. Near the event horizon of a black hole, the violent curvature of spacetime affects the quantum vacuum. The pairs of virtual particles that normally appear and annihilate become separated by the horizon. One particle falls in, the other escapes. The escaping particle carries energy away from the black hole. Over vast periods of time, this energy loss causes the black hole to slowly shrink. A stellar mass black hole would take longer than the current age of the universe to shrink appreciably, and far longer to evaporate completely. But in principle, given enough time, it evaporates entirely. It's gone. And this creates a problem of extraordinary depth. The state of a physical system contains information. Information about what the system is made of, how the particles are arranged, what their velocities are, every detail about the configuration. In quantum mechanics, information is sacred. It is conserved. The laws of quantum mechanics are, in the technical language, unitary, meaning they preserve information. If you know the precise quantum state of a system at one moment, and you know the laws of physics, you can in principle reconstruct the precise quantum state at any other moment. Information is never lost, it is only rearranged, but Hawking radiation appears to violate this. If a black hole forms from a specific configuration of matter, information about that configuration is, in principle, encoded in the quantum state of the matter. But as the black hole evaporates, what comes out is Hawking radiation, which is thermal radiation, which is random. It carries no information about what fell in. It looks exactly the same regardless of what the black hole was made of. If the black hole evaporates completely, and if Hawking radiation carries no information, then the information about what made the black hole is gone. Permanently, irreversibly, it has been destroyed. This violates unitarity. It contradicts one of the deepest principles of quantum mechanics. It says information can be lost, which the laws of physics, as we understand them, do not allow. This is the black hole information paradox. And it is one of the most fiercely debated problems in theoretical physics. Different physicists have taken different positions. Hawking originally argued that information is indeed lost. That black hole evaporation genuinely destroys information, and that this requires a modification of quantum mechanics. Others, including Gerard T. Hooft and Leonard Susskind, argued strenuously that information must be preserved, that something we don't understand must carry the information out in the Hawking radiation. The controversy led to one of the most spectacular bets in physics. In 1997, Hawking and Kip Thorne bet John Preskill that information was lost in black holes. Preskill bet it was preserved. In 2004, Hawking publicly conceded the bet. What changed his mind was a set of developments in string theory. particularly the development of the anti-de Sitter conformal field theory correspondence, known as AD-SCFT. This is a duality, a precise mathematical equivalence between a theory of gravity in a curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime. The boundary theory is manifestly unitary. Information is manifestly preserved, and because the two theories are mathematically equivalent, information must also be preserved in the gravity theory. Black hole evaporation must somehow, in some way we don't fully understand, preserve information. This result is now accepted by most physicists working on quantum gravity. Information is preserved, but the mechanism is mysterious. How does information get out of a black hole? How does it get encoded in the Hawking radiation? This is still not fully understood. It involves ideas about quantum entanglement, about the information content of the event horizon, about the way the black hole interior is described in quantum mechanics. These ideas are at the frontier of research. But here's what this has to do with our question. The AD-SCFT correspondence suggests something profound about the nature of reality. It suggests that a quantum gravity theory in a higher dimensional space is equivalent to a non-gravitational theory on the boundary of that space. Gravity in this picture is not fundamental, it is emergent. It arises from the quantum entanglement structure of a lower dimensional system. This is called holography. The idea that the information content of a volume of space is encoded on its boundary surface, just as a hologram encodes a three-dimensional image on a two-dimensional surface. If holography is correct, then spacetime itself, space and time, gravity, the fabric of reality as we experience it, all of this might be emergent. It might be a description that arises from something more fundamental that doesn't have space and time. This connects to the question of origins in a striking way. If spacetime is emergent, then the question of what came before spacetime is not the right question. What we should be asking is, what is the more fundamental theory from which spacetime emerges? And the beginning of spacetime, what we call the Big Bang, is then a question about how the emergent spacetime description arises from the more fundamental non-spatial, non-temporal description. In this picture, the Big Bang is not an event in time. It is the beginning of time. And time is not fundamental. It is emergent. And what it emerges from is a quantum information structure, a pattern of entanglement and correlations that exists in a description without space or time. We don't have this theory. We have glimpses of it from AD-SCFT, from loop quantum gravity, from the study of quantum information and entanglement. But we don't have the full picture. What we have is a direction. And the direction points toward a revolution in our understanding of reality that would make everything we've discussed tonight look like small steps toward an incomprehensibly deep truth. Let's try to see that truth, even dimly, even partially. Let's ask what it would mean for space and time and everything to be emergent. And let's see if we can even partially answer the question we started with. There is a possibility that most physicists find uncomfortable to consider, but that the mathematics keeps pushing toward. A possibility that, if correct, would require the most fundamental revision in our understanding of reality since quantum mechanics itself. The possibility is this: the universe might not have existed before it was observed, not in the trivial sense that we need instruments to learn about it. In the deep sense that quantum mechanics applies not just to subatomic particles, but to spacetime itself. and that the act of observation is what collapses the quantum possibilities into the classical reality we experience. This is the many worlds interpretation of quantum mechanics applied cosmologically, and it leads directly to a disturbing picture of the Big Bang. In the standard Copenhagen interpretation of quantum mechanics, a quantum system exists in a superposition of states until it is measured. Before measurement, the particle doesn't have a definite position. It has a wave function that assigns probabilities to different possible positions. Measurement collapses this wave function. The particle acquires a definite position. This interpretation works beautifully for laboratory experiments. But it has a problem when you try to apply it to the universe as a whole, because who measures the universe? What collapses the wave function of the cosmos? In the Copenhagen interpretation, there must always be an observer outside the system. But there is nothing outside the universe. The Copenhagen interpretation, taken literally, cannot apply to cosmology. Hugh Everett's many worlds interpretation solves this problem by eliminating collapse entirely. In the many worlds interpretation, there is no collapse. The wave function never collapses. It evolves according to the Schrödinger equation always and everywhere. When a measurement occurs, the wave function of the measuring apparatus becomes entangled with the wave function of the measured system. All outcomes occur. The universe branches. After a measurement of a particle that could be in two places, there are two branches of the universe. In one, the particle is here. In the other, it is there. Both are equally real. The observer in each branch experiences only one outcome because they are part of one branch, but both branches exist. The wave function of the universe, in the many worlds interpretation, is a vast superposition of all possible histories, all possible outcomes of every quantum event at every moment in every place, all of them occurring simultaneously, all of them real. Our universe, our history, our sequence of events is one branch of this enormous structure. The Big Bang that gave rise to our universe is the branch point from which our particular history diverged from other possible histories. What existed before the Big Bang in this picture is not nothing and not some prior universe in the same sense as ours. It is the pre-branching quantum state, the wave function before it differentiated into the particular branch that gave rise to our cosmos. This is the no-boundary proposal, again, but now with the full quantum mechanical context. Hawking and Hartle's picture of a universe that emerged from a regime where time was Euclidean, where there was no before, can be understood as describing the pre-branching quantum state of the universe. A state from which all possible cosmological histories emerged, of which ours is one. In this picture, asking what came before the Big Bang is like asking what was there before the wave function of the universe branched into our history. And the answer is the full wave function, the superposition, the pre-classical state from which our particular branch of reality emerged. This is not satisfying to everyone. The many worlds interpretation raises its own deep questions about the nature of probability, about the ontological status of the branches, about what it means for something to be real if it exists in a branch we can't observe. These debates have been going on for 60 years and are not resolved. But what these ideas collectively point toward is something important. The question of what came before the Big Bang is not simply a question about a prior state of matter and energy in a prior time. It is a question about the nature of the quantum state of reality itself, about whether time is fundamental or emergent, about whether spacetime is the ultimate description or an approximation to something deeper? And these questions are pushing physics toward places that would have seemed like philosophy not very long ago. The boundary between physics and philosophy is eroding at the frontier of quantum gravity. The deepest questions about the beginning of the universe are also the deepest questions about the nature of reality, the nature of time, the nature of information, the nature of observation. Now, let's step back from all of this abstraction and ask a different kind of question. Can any of this be tested? Is there any way to distinguish between these proposals empirically? Is there any observation we could make that would tell us whether the universe bounced or emerged from nothing, or has always existed, or is one branch of a larger quantum structure? The answer is possibly. And the search is already underway. Every proposal for what came before the Big Bang makes some prediction about what the universe should look like today. If the predictions are different enough, and if our instruments are sensitive enough, we might be able to distinguish between the proposals. We might not be able to go back before the Big Bang, but we might be able to read its echoes. The primary window we have into the earliest universe is the cosmic microwave background. The CMB is the oldest light in the observable universe. It was emitted 380,000 years after the Big Bang, and it carries imprinted on it the pattern of density fluctuations that existed at that time. Those density fluctuations are the seeds of all the structure we see in the universe today. The galaxies and galaxy clusters and cosmic filaments all grew from tiny overdensities in the early universe that were amplified by gravity over billions of years. The pattern of these density fluctuations, the way their sizes and strengths are distributed, is described by what physicists call the power spectrum of the CMB. And different proposals for the origin of the universe predict different power spectra. Cosmic inflation, in its simplest forms, predicts a nearly scale-invariant power spectrum. This means that density fluctuations of all sizes are present in roughly equal amounts. The Planck satellite's observations of the CMB are consistent with this prediction. This is one of the strongest pieces of evidence for inflation. But inflation also makes more specific predictions. It predicts a spectrum of gravitational waves, ripples in spacetime generated during the inflationary epoch. These primordial gravitational waves would leave a specific imprint on the CMB in the polarization of the microwave photons. This imprint is called B-mode polarization. Detecting B-mode polarization from inflation would be smoking gun evidence for the inflationary epoch. And the amplitude of the signal, how strong it is, would tell us about the energy scale at which inflation occurred. This would constrain which models of inflation are correct, and in turn constrain what the pre-inflationary universe might have looked like. Multiple experiments are currently searching for this signal. The Bicep Keck Array at the South Pole. The CMB-S4 experiment, which is the planned next-generation CMB observatory. The Lightbird satellite, planned by Japan's space agency. All of these are looking for the imprint of primordial gravitational waves on the CMB polarization. If they find it, the implication is that inflation happened at a certain energy scale. If the energy scale is near the Planck scale, that would suggest inflation happened very close to the quantum gravitational era, and the connection between inflation and pre-Big Bang physics would be direct. Loop quantum cosmology, as I mentioned earlier, predicts specific modifications to the power spectrum of the CMB. These modifications arise from the way quantum gravity effects in the pre-bounce universe leave their imprint on the state of the universe just after the bounce. The predictions are subtle, affecting primarily the very largest angular scales in the CMB. Current CMB data is consistent with these predictions, but not conclusively in favor of them. The largest scales are also the ones where cosmic variance, the fundamental limit on our ability to extract statistical information from a single sky, is most limiting. We only have one universe to observe. We can't repeat the experiment. The uncertainty in the largest scale CMB observations is limited not by our instruments, but by the fact that there's only so much sky to measure. Future CMB experiments, including those looking at polarization, might provide better constraints, but detecting the specific signatures of loop quantum cosmology in the CMB will require extraordinary sensitivity. There is another probe of the very early universe that is, in some ways, even more direct than the CMB: gravitational waves. The CMB is the oldest electromagnetic radiation in the universe. But the universe has been transparent to gravitational waves since the very first moments after the Big Bang. Gravitational waves can travel through the dense early plasma that blocked electromagnetic radiation. If gravitational waves were generated in the first instance of the universe, they are still traveling through space today, unchanged by the billions of years of expansion. These primordial gravitational waves would have a spectrum of frequencies determined by the physical processes that generated them. Inflation would generate one spectrum. A phase transition, like the kind predicted by some models of the early universe, would generate a different spectrum. A bounce, as predicted by loop quantum cosmology, would generate yet another. Current gravitational wave detectors, like LIGO and Virgo, are not sensitive to the very low-frequency gravitational waves from the early universe, but future detectors are designed to be. The LISA mission, a space-based gravitational wave detector planned for launch in the 2030s, will be sensitive to millihertz frequencies, much lower than ground-based detectors. It could detect gravitational waves from the early universe. The Einstein telescope, planned for Europe, and the Cosmic Explorer, proposed for the United States, will be far more sensitive than current ground-based detectors, extending the observable frequency range and improving sensitivity. If we detect a stochastic background of gravitational waves at the frequencies predicted by specific models of the early universe, we would have direct evidence of physical processes that occurred in the first instance after, or potentially before, the Big Bang. There are also observations coming from an entirely different direction: the study of the largest scale structure of the universe. Galaxies are not uniformly distributed through space. They are organized into filaments and sheets surrounding enormous voids. This web-like structure, called the cosmic web, was generated by the same density fluctuations that created the CMB anisotropies. By mapping the distribution of galaxies across enormous volumes of space, cosmologists can measure the statistical properties of these fluctuations and compare them to theoretical predictions. Surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, the Euclid mission from the European Space Agency, and the Vera Rubin Observatory's Legacy Survey of Space and Time are all mapping the universe's large-scale structure in increasing detail. These maps are compared to theoretical predictions from different models of the early universe. The constraints from large-scale structure are complementary to the CMB constraints. They probe different scales, different redshifts, different aspects of the primordial fluctuations. Together, they paint an increasingly detailed picture of the initial conditions of the universe, which in turn constrains the physical processes that set those conditions. None of these observations can directly show us what happened before the Big Bang, but they can rule out some proposals, support others, and narrow the range of possibilities. They can tell us the story of the earliest moments we can access observationally, which is not the Planck time but the end of inflation, the era of nucleosynthesis, the decoupling of photons. Each of these epochs has left its imprint in the data. And there is one more observational frontier that has not yet been exploited, but that holds enormous promise: neutrino astronomy. Neutrinos are the most weakly interacting massive particles in the Standard Model. They pass through ordinary matter almost without interaction. The universe became transparent to neutrinos about 1 second after the Big Bang, much earlier than it became transparent to photons. A cosmic neutrino background exists, analogous to the cosmic microwave background, but older. These relic neutrinos were last scattered when the universe was about 1 second old. They carry information about the universe at an earlier epoch than the CMB photons. Detecting these relic neutrinos and measuring their properties would give us a window into the universe at an earlier time than any electromagnetic observation can access. The challenge is extraordinary. The relic neutrinos are cold, at a temperature of about 195 Kelvin, and extraordinarily weakly interacting. No current technology can detect them. But proposed experiments like Ptolemy, which aims to detect relic neutrinos through their capture by tritium, offer a glimpse of what might eventually be possible. If we can detect the cosmic neutrino background, measure its temperature and density, look for deviations from simple predictions, we would have a new window into the first second of the universe's history. A window that might contain echoes of whatever came before. The search is ongoing, the tools are being built, the data is accumulating, and what's driving all of it is the same thing that's driven science for centuries: the refusal to accept that some questions are unanswerable, the insistence on asking, even when the asking is hard. Let's take a step back from the abstract mathematics of quantum gravity and ask a question that cuts closer to the bone. Why does the universe have the properties it has? This is not the same as asking what came before the Big Bang. It's asking why the Big Bang, when it occurred, produced a universe like this one, rather than one of the countless other universes that the laws of physics seem to permit. The question sounds like philosophy, but it has a physical answer, or at least a set of physical answers, and those answers are deeply connected to the question of origins. Consider the cosmological constant. This is the term in Einstein's equations of general relativity that acts like an energy density associated with empty space. It represents the energy of the vacuum. We've already mentioned that quantum field theory predicts a vacuum energy that is about 120 orders of magnitude larger than what we observe. This is the worst prediction in the history of physics. The predicted value is enormous. The observed value is tiny, but the observed value is not zero. The observed cosmological constant is small, almost zero, but crucially not quite zero. And this tiny non-zero value has an enormous consequence. It drives the accelerating expansion of the universe. The dark energy that is pushing the universe apart faster and faster is the cosmological constant in action. Now here is the extraordinary thing. The value of the cosmological constant in our universe is almost perfectly tuned for life. If the cosmological constant were significantly larger than its actual value, the universe would have expanded so rapidly that matter could never have clumped together into galaxies. The universe would be filled with a dilute soup of particles, too spread out to ever form stars, planets, or life. We would not exist. If the cosmological constant were significantly smaller, specifically if it were large and negative, the universe would have recollapsed long before galaxies had time to form. Again, no stars, no planets, no life. The range of cosmological constant values compatible with the existence of structures like galaxies and stars is extraordinarily narrow. Our universe sits inside that narrow range. Whether this is a coincidence, a physical necessity, or evidence of selection from a large ensemble of universes is one of the deepest questions in cosmology. The same kind of fine-tuning argument applies to several other fundamental constants of physics. The mass of the electron, the ratio of the electromagnetic force to gravity, the number of large spatial dimensions, the properties of the strong nuclear force, which determines whether atomic nuclei are stable. Many of these constants appear to be tuned to values that allow the complexity necessary for life. Change any of them significantly, and you get a dead universe. A universe of nothing but hydrogen, or a universe that collapses in seconds, or a universe where no complex chemistry is possible. This observation is called the fine-tuning problem, and it sits at the intersection of physics, cosmology, and philosophy in a way that makes many physicists uncomfortable. There are three broad categories of response to the fine-tuning problem. The first is that it's coincidence. Our universe has the constants it has. We observe it because we're in it. If it were otherwise, we wouldn't be here to ask the question. This is the anthropic principle in its weakest form. It doesn't explain the fine-tuning. It just notes that observers necessarily find themselves in a universe compatible with observers. The second is that there's a deeper theory that explains the constants, a more fundamental physics that derives the values of the constants from first principles, making them necessary rather than contingent. In this case, the universe would have to have the constants it has. There's no fine-tuning because there's no freedom. The constants are what they must be. The third is the multiverse. If there is an enormous ensemble of universes, each with different values for the constants, then some of them will have constants compatible with life. We necessarily find ourselves in one of those because we exist. The fine-tuning is no more mysterious than the fact that we're on a planet with liquid water in the habitable zone of a stable star. The universe seems fine-tuned for us because we live in the fine-tuned region. The multiverse explanation for fine-tuning is powerful and disturbing in equal measure. Powerful because it genuinely resolves the fine-tuning problem without requiring any deep, unexplained coincidence. Disturbing because it seems to remove the explanatory power of the constants. If they're just accidents of our particular bubble, there's nothing to explain them. And if there's nothing to explain them, the project of deriving the constants from a deeper theory seems pointless. This is a genuine tension in modern physics. The multiverse, which emerges naturally from eternal inflation, from the string landscape, provides a powerful framework for explaining fine-tuning. But it also potentially undermines the traditional program of physics, which is to find deeper and deeper explanations for why things are as they are. But here's the connection to our central question. The fine-tuning problem is not separate from the question of what came before the Big Bang. It's part of the same complex of questions. If our universe is one of many, nucleating from an eternally inflating background, then the question of why our universe has the constants it has becomes the question of what determines which point in the landscape our bubble occupies. And that question leads back to the structure of the multiverse, which leads back to the question of what the multiverse is, where it came from, and whether it has always existed. If the constants are explained by a deeper theory that derives them from first principles, then we need to understand that deeper theory, which is presumably some form of quantum gravity or unified field theory. And understanding that theory would presumably also illuminate the question of what came before the Big Bang, because the deeper theory would govern the pre-Big Bang regime. Every thread leads to the same place. The deepest questions in physics are connected. The origin of the universe, the fine-tuning of the constants, the nature of dark energy, the structure of quantum gravity, these are not separate mysteries. They are facets of the same mystery. And the mystery is this: why does the universe permit complexity? Why, out of all the possible mathematical structures that could be physical reality, do we find ourselves in one that allows stars and planets and chemistry and life, and the experience of asking questions about our own existence? This question cannot be answered by physics alone, but physics can make progress on it. The multiverse, the landscape, the anthropic principle, the fine-tuning problem, these are all genuine scientific ideas that can be studied, whose predictions can be compared with observations, whose implications can be worked out. And working them out leads inevitably to the edge of what physics can currently describe, to the boundary between the known and the unknown, to the questions that define the frontier. The silence before the Big Bang is not just a question about time. It's a question about why this particular universe, with these particular laws, exists at all. And that question is the most profound one that physics has ever faced. John Archibald Wheeler was one of the most creative physicists of the 20th century. He worked with Einstein. He coined the term black hole. He developed the Wheeler-DeWitt equation we discussed earlier. And in the later years of his life, he became obsessed with a question that most physicists consider too dangerous to ask. Is the universe brought into existence by observation? This is not idle speculation. It grows directly from the interpretation of quantum mechanics, and it leads to one of the most radical proposals about the relationship between the before and the after, between the observer and the observed. In quantum mechanics, the act of measurement plays a special role. Before measurement, a quantum system exists in a superposition of states. After measurement, it is in a definite state. Something happens at measurement that is not described by the ordinary quantum mechanical evolution equation. This is the measurement problem. It has been debated since quantum mechanics was formulated in the 1920s, and it is not resolved. Different interpretations of quantum mechanics treat measurement differently. In the Copenhagen interpretation, the wave function collapses upon measurement, but there's no physical description of how. In the many worlds interpretation, the observer becomes entangled with the system, and there's no collapse, just branching. In other interpretations, additional variables or modifications to quantum mechanics or specific decoherence mechanisms are invoked. Wheeler pushed the measurement problem to its cosmological extreme. He proposed that the universe is what he called a participatory universe, that the universe does not exist independently of observation, that in some deep sense, observers are needed to bring the universe into existence. He illustrated this with a thought experiment called the delayed choice experiment. In standard quantum mechanics, whether a photon behaves as a wave or a particle depends on how it is measured. If you measure which path it took, it behaves as a particle and went through one path. If you don't measure which path it took, it behaves as a wave and interfered with itself. Wheeler extended this. What if the measurement choice is made after the photon has already been traveling for billions of years? What if a photon from a distant quasar has been traveling for billions of years, and we only now decide how to measure it? Does our present choice retroactively determine how it behaved billions of years ago? The answer from quantum mechanics is, in a sense, yes. The photon didn't take a definite path until a measurement was made. The measurement collapses the superposition. But this collapse has no preferred time. It doesn't happen at a specific moment in the photon's history. The photon's history is indeterminate until measured. Our present observation, in a precise quantum mechanical sense, participates in determining the photon's past. The delayed choice experiment has been performed in the laboratory with photons and atoms. The results confirm quantum mechanical predictions. The observation made now does, in the relevant quantum mechanical sense, determine the past behavior of the particle. Wheeler took this seriously at the cosmological level. Observations made now, he argued, might be participating in bringing the universe into existence. Not creating it out of nothing, but collapsing its quantum superposition into the particular history we observe. This is called the participatory anthropic principle, and it is deeply controversial. Most physicists consider it too speculative, too close to mysticism, too far from anything that can be tested. But it is a logical extension of quantum mechanics applied at the cosmological scale, and it raises a question that connects directly to our central question. If observations are needed to determine the past of the universe, what observations were there before observers evolved? Before there were any conscious beings to measure anything, what determined the universe's history? Wheeler's answer, in his later writings, was that the universe bootstrapped itself into existence. That the very existence of conscious observers billions of years after the Big Bang, capable of making quantum mechanical observations, somehow retroactively determined the quantum history of the universe that led to those observers. This is a circle. The universe produces observers. The observers, by observing, participate in bringing the universe into the form that produced them. The universe and its observers create each other. Now, to be very clear, mainstream physics does not accept this picture. Most physicists working on quantum cosmology, quantum gravity, and cosmology in general work within frameworks that do not require this kind of observer dependence of the universe's history. The decoherence program, for example, shows how quantum superpositions can effectively collapse into classical histories through interaction with the environment, without any need for conscious observers. The many worlds interpretation avoids the measurement problem entirely by denying collapse, but Wheeler's ideas point to something real and deep. The relationship between observer and observed, between consciousness and physical reality, is not fully resolved by any current interpretation of quantum mechanics. And when you scale quantum mechanics up to the universe, when you ask about the quantum state of the cosmos as a whole, the question of what counts as observation, of where the wave function collapses and why, becomes genuinely deep. There is a tradition in philosophy, going back at least to Berkeley in the 18th century, of arguing that existence requires observation. That to be is to be perceived. Physics has generally resisted this idealism, insisting that the physical world exists independently of minds, that it has definite properties independent of observation. But quantum mechanics complicates this. The wave function assigns probabilities to measurement outcomes. Before measurement, there are no definite values, only superpositions. The definiteness of the world emerges, somehow, from the interaction between quantum systems and observers. Exactly what this means for the existence of the universe before any observers existed is not clear. These questions are at the edge of what science can currently address. They blur the boundary between physics and philosophy. Many physicists would say they're not physics at all. Others would say they're the deepest physics there is. What they contribute to our question of what came before the Big Bang is this: the question of what exists before observation, the question of what the pre-observed universe was like, is connected to the deepest interpretational questions in quantum mechanics. If the universe requires observers to have a definite history, then the question of what it was before observers existed is not a simple factual question. It's a question about the quantum mechanics of closed systems, about what it means for something to exist without being observed, about the relationship between possibility and actuality at the most fundamental level. These are not idle questions. They are real physics questions, even if they look like philosophy. And their answers, when they come, will be part of the picture of what came before the Big Bang. We've been talking about the beginning of time, but to really understand what that means, we need to understand something about the nature of time that is deeply counterintuitive and almost never discussed. The fundamental laws of physics are time-symmetric. They work equally well forward and backward in time. Let me say that again, because it's important. Take any process described by the laws of physics. The motion of a planet in its orbit, the collision of two billiard balls, the interaction of two electrons. If you run the movie backward, if you reverse the direction of time, the backward process is also consistent with the laws of physics. There is no physical law that distinguishes the forward from the backward direction. This is remarkable because our experience is profoundly asymmetric in time. The past is different from the future. Eggs break but don't unbreak. Ice melts but doesn't unmelt. People age in one direction. Causes precede effects. Memory records the past but not the future. The arrow of time points clearly in one direction. How can the fundamental laws be time-symmetric when our experience is so strongly time-asymmetric? The answer is entropy, and entropy connects directly to the question of what came before the Big Bang. Entropy is a measure of disorder, of the number of ways a physical system can be arranged while still looking the same at the macroscopic level. A broken egg has higher entropy than an intact egg because there are many more ways to arrange the molecules of the broken egg while still having a broken egg, compared to the ways to arrange them while having an intact egg. The second law of thermodynamics tells us that entropy tends to increase over time. Isolated systems evolve from lower entropy to higher entropy. This gives time its arrow. The future is the direction in which entropy increases, but here's the puzzle. If the fundamental laws are time-symmetric, why does entropy increase in one direction rather than the other? Why doesn't entropy sometimes decrease? What breaks the symmetry? The answer, disturbing in its depth, is the low entropy of the initial state. The universe started in a state of extraordinarily low entropy. The Big Bang was smooth, uniform, featureless at the level of the CMB fluctuations, extraordinarily ordered. As the universe has evolved, entropy has increased, structure formed, stars burned, entropy rose. The arrow of time, the reason the future feels different from the past, is ultimately traceable to this single fact. The universe started in a state of low entropy. We are moving away from that state. That's what time is. But this just pushes the question back. Why did the universe start in such a low entropy state? This is one of the deepest questions in physics, and it's directly connected to the question of what came before the Big Bang. Roger Penrose, one of the great mathematical physicists, has argued for decades that the low entropy initial state of the universe is the most profound mystery in physics. He quantifies it as follows. The entropy of the observable universe today is enormous. The number of ways the universe could be arranged, while looking as it does now, is approximately 10 to the power of 10 to the power of 123, an almost inconceivably large number. But the entropy of the early universe, the state from which this evolved, is incomparably smaller. The initial state was selected from among an almost incomprehensibly large space of possibilities, and it happened to be almost perfectly ordered. Why? What mechanism produced this particular initial condition? One answer is that the initial condition had to be fine-tuned. That without some explanation we don't have, the universe just happened to start in an extraordinarily low entropy state. This seems deeply unsatisfying. It's just asserting a brute fact about the initial conditions with no underlying explanation. Another answer is inflation. Inflation naturally produces a smooth, uniform universe as its output. Regardless of what the initial conditions were, inflation drives the universe toward the smooth, flat state that the CMB observations confirm. So in some sense, inflation explains the low entropy initial state by connecting it to the generic output of the inflationary mechanism. But inflation itself started in some state. What was the entropy of the pre-inflationary state? Was it low? If so, we've just pushed the problem back. And if the pre-inflationary state was high entropy, how did inflation produce a low entropy output from a high entropy input? That would seem to violate the second law. There is a subtlety here. Inflation produces a smooth, low entropy matter distribution. But inflation also produces an enormous volume of spacetime. The entropy budget of spacetime itself is different from the entropy budget of the matter within it. The total entropy of the universe, including both matter and spacetime, may actually increase during inflation, even as the matter entropy decreases. Inflation might be consistent with the second law when you account for gravitational entropy properly. This brings us to Penrose's own proposal, which he calls conformal cyclic cosmology. Penrose argues that the universe has no beginning in the usual sense. Instead, it goes through eons, each eon beginning with a big bang and ending with a heat death, the universe expanding forever until all black holes have evaporated and all matter has decayed, leaving nothing but photons in an exponentially expanding, infinitely thin dilute cosmos. But here's the extraordinary insight. In the very far future, when the universe has expanded so much that the only things left are photons traveling through empty space, the concept of scale disappears. Photons are massless. They don't have a sense of size. In the physical description of a universe containing only massless particles, there is no way to define a unit of length. The universe becomes conformally flat in the technical sense, meaning it forgets its size. Penrose argues that this conformally flat, infinitely dilute future universe is mathematically identical to the conformally flat, smooth initial state of the next eon's Big Bang. The infinite future and the next eon's Big Bang are the same point in a mathematical sense. The death of one universe is the birth of the next. In this picture, the low entropy initial state of each universe is explained by the structure of the previous eon's infinite expansion. The universe doesn't start from an arbitrary low entropy initial condition. It inherits its initial condition from the conformal geometry of the previous eon's end state. Penrose's proposal is speculative and controversial. Most physicists are skeptical of it. There are technical objections. There are questions about whether the conformal matching of past infinity to future infinity is actually mathematically consistent in our universe. But it represents a genuine attempt to address the arrow of time problem, to explain why the universe started in a low entropy state by connecting the beginning to a prior eon. And in doing so, it provides one more picture of what might have come before our Big Bang. In Penrose's conformal cyclic cosmology, what came before was a prior universe in its final, infinitely thin, infinitely dilute phase. Not a rich, structured universe like ours, a ghost, a mathematical echo, an infinitely expanded photon gas from which our universe's smooth initial conditions were inherited. Strange but internally consistent, and connected to the deepest question in physics about why time flows the way it does. The arrow of time and the question of what came before are the same question. Both ask about the relationship between the present state of the universe and whatever preceded it. Both are answered or pointed at by the same physics. The physics of entropy, of quantum gravity, of the structure of spacetime at its boundaries. Everything connects. The universe is not a collection of separate mysteries. It is one mystery, seen from different angles. We have traveled a long way tonight. We started with a question that seems simple and immediate. What existed before the Big Bang? And we have followed it through the structure of spacetime, through the mathematics of quantum gravity, through inflation and loops and strings and bounces and nothing, until we've arrived at a place where the question itself is not what it seemed. Let me try to put all of this together, not as a definitive answer because there isn't one, but as an honest account of where physics stands and of what the question is really asking. The first thing we've learned is that the question contains assumptions. The most important assumption is that time extends backward through the Big Bang, that there was a before in the same sense that there is a before breakfast. This assumption is not obviously correct. The laws of physics, as we understand them, break down before the Planck time. We cannot meaningfully apply the concept of time to the universe at densities above the Planck density. The word before is a temporal word. If time breaks down, before might too. The Hartle-Hawking no-boundary proposal takes this seriously and proposes that the boundary of time is like the South Pole. There is no before not because there was nothing, but because the concept of before has a boundary, just as south has a boundary. The question is not unanswerable. It is inapplicable, in the same way that asking what's south of the South Pole is inapplicable. The second thing we've learned is that if time does extend backward through the Big Bang, or if something like time applied in the pre-Big Bang regime, then several coherent pictures exist of what might have been there. Eternal inflation places our Big Bang in a larger context, a multiverse of bubble universes nucleating from an eternally inflating background. Before our Big Bang, the background. but what was before the background is a question the theory doesn't definitively answer. Loop quantum cosmology replaces the singularity with a quantum bounce. Before our Big Bang, a contracting universe that collapsed to a maximum density and then reversed. Before that contracting universe, perhaps an even earlier expansion. And before that, either an infinite chain of bounces or a beginning that loop quantum cosmology does not currently describe. String theory contributes the landscape and the pre-Big Bang scenario, the possibility of a contracting dilute universe preceding our expanding one, or the possibility of a multiverse populated by different string vacua with different physical laws. Vilenkin's creation from nothing proposes that the universe tunneled into existence from a state with no space, no time, no matter. A state that has no before because it has no time. The Wheeler-DeWitt equation describes a timeless quantum state of the universe from which the experience of time emerges as a relational feature of the internal correlations. In this picture, there is no before the Big Bang because before presupposes time, and the fundamental description is timeless. The third thing we've learned is that the question of what came before the Big Bang is connected to some of the deepest unsolved problems in physics. The problem of quantum gravity, the problem of time, the problem of the arrow of time, the problem of why anything exists at all. These aren't peripheral questions, they're central to physics. And the fourth thing we've learned is that this isn't hopeless. The proposals make predictions. The predictions can be tested, at least in principle, through observations of the CMB, gravitational waves, large-scale structure, neutrino backgrounds. Future experiments might be sensitive enough to distinguish between them. The question of what came before the Big Bang is not merely philosophical. It is at least partially a scientific question with an empirical dimension. But there is something else worth saying, something that is not often said in the context of scientific questions, but that is genuinely relevant here. The question of what came before the Big Bang touches something deep in human beings. It is not just an intellectual puzzle. It is an existential question. It asks about the ultimate context of our existence. About whether there was something before everything we know, or whether everything we know is all there is. And there is something profound in the way that the deepest physics keeps circling back to the answer, that the question may be misconceived, that the universe may not have had a beginning in the same sense that an event in history has a beginning. That time itself may be something that emerged, that was not always there. This is not an argument against asking the question, quite the opposite. The fact that asking the question leads to such deep and unexpected places is exactly why it should be asked. The question of what came before the Big Bang has driven the development of quantum gravity, of inflationary cosmology, of the study of quantum information and holography. It has been extraordinarily productive. But there is a kind of peace available in the deepest answer. Not the peace of having the answer, but the peace of having understood the question more deeply, of having followed it to the point where it transforms into a different, deeper question, of having seen that the question contains assumptions about the nature of time that may not be valid at the boundary of time. What came before the Big Bang? Maybe nothing, in the deep geometric sense that south is nothing at the South Pole. Maybe a prior contracting universe. Maybe an eternally inflating background. Maybe a timeless quantum state. Maybe a mathematical structure from which spacetime and time themselves emerged. Maybe a question that only arises because we're embedded in a universe with a beginning. looking backward toward an edge we cannot cross. Maybe the deepest answer is that the universe is a mathematical object with a finite past in one direction, and that the existence of that past edge, the beginning of time, is as fundamental a feature of reality as the existence of the universe itself. What we know for certain is this: the universe had a beginning. That beginning was preceded, in some sense, by conditions we cannot yet describe with the physics we have. And the attempt to describe those conditions is pushing physics toward a revolution in our understanding of space, time, information, and reality that may be as deep as any revolution that has come before. We are living at the beginning of that revolution, not at its end. The answers are not in. The experiments are still running. The theories are still being developed. The question is alive, and it is doing what the best questions do, changing what we think we know. There is a particular kind of beauty in questions that resist answers. Not all unanswered questions are beautiful. Some are just hard, waiting for the right technique or the right data. But some questions are beautiful in the way that a deep pool is beautiful. You can see into it. You can see the light bending through it, the way the bottom distorts and shimmers, but you cannot see the bottom. And the depth itself is part of what you're looking at. The question of what came before the Big Bang is a pool of that kind. We can see into it. We can see general relativity bending and breaking at the Planck scale. We can see quantum mechanics suggesting that space and time are not fundamental. We can see the mathematics of string theory describing a landscape of possible universes. We can see loop quantum cosmology replacing the singularity with a bounce. We can see inflation pointing toward an eternally inflating background that preceded our universe. We can see all of this, but the bottom, the truly fundamental answer, is still shimmering out of reach, and maybe that's appropriate. Maybe the question of why there is something rather than nothing, the question of the absolute beginning of everything, is one that will always resist final answer. Not because our instruments aren't good enough or our theories aren't sophisticated enough, but because the question itself points beyond any possible answer. Any answer will describe some state, some structure, some. And you can always ask what came before that. Leibniz understood this. That's why he framed the question the way he did. Why is there something rather than nothing? The nothing in that question is not a physical state. It's not a vacuum or a quantum foam or a pre-geometric regime. It's a genuine absolute nothing, a logical nothing that cannot be the subject of physics. Physics can push the question back, further and further. From our universe to the eternal inflation that preceded it, to the quantum gravitational regime that preceded that, to the timeless wave function that contains it all. But at each step, there is still something, still some mathematical structure, some law, some principle. The final why, if there is one, cannot be answered by physics. It can only be pointed at. This is not a failure of science. It is an honest recognition of the limits of the scientific method. Science is the most powerful tool humanity has for understanding the physical world. It has produced miracles, the mapping of the human genome, the detection of gravitational waves from colliding black holes a billion light-years away, the discovery of the Higgs boson, the sequencing of the Big Bang's afterglow to parts in 100,000. But science asks how. It describes mechanisms. It discovers laws. It connects observations to theories. It cannot answer the ultimate why. Why does anything exist at all? Why are there laws of physics rather than no laws? Why does mathematics describe reality? These questions are real. They are not silly. They are not resolved by any scientific theory. but they are also not the questions we have been trying to answer tonight. Tonight, we have been asking something more modest but still extraordinary. Given that there is a universe, what came before it? What were the conditions from which it emerged? What is the structure of time at its boundary? And to those questions, science has real things to say. Incomplete things, speculative things, things that will need revision as new data arrives. But real, substantive, mathematically careful things. What came before the Big Bang? Here is the most honest summary. The concept of before may not apply at the boundary of time. Time may have a beginning in the same geometric sense that space has an edge, a boundary beyond which the concept of position ceases to apply. This is the no-boundary proposal, and it is a genuine mathematical possibility that cannot be dismissed. If time does extend backward, or if something like time applies before our Big Bang, then the most likely candidates are a quantum bounce in which our Big Bang emerged from a prior contracting universe, an eternally inflating background from which our universe nucleated as a bubble, a timeless quantum state of reality from which time itself emerged as an emergent feature, or a quantum tunneling event from a state of no space and no time. Each of these proposals is incomplete. Each has unsolved problems. None has been confirmed by observation. But each is a serious scientific hypothesis, not a fantasy. And perhaps most importantly, each of these proposals changes what it means to ask the question. Each of them reveals that the question of what came before is not just asking about a prior state. It is asking about the nature of time, the nature of space, the nature of the laws of physics themselves. The question that sounds like a simple inquiry into history turns out to be a question about the deepest structure of reality. And that, more than any specific answer, is why the question matters. Not because we expect to resolve it soon, not because there is a clear path from our current knowledge to a definitive answer, but because asking it, following it as deeply as we can go, taking it seriously even when it becomes strange and mathematical and abstract, is what drives the frontier of physics forward. Every proposal we discussed tonight, no boundary cosmology, eternal inflation, loop quantum cosmology, string landscape, creation from nothing, the emergence of time, every one of these ideas was developed by physicists who took the question seriously, who refused to dismiss it, who insisted on following the mathematics wherever it led, even when it led to places that seemed absurd or incomprehensible. The universe does not owe us comprehensibility. It does not arrange itself to be easily understood. The most fundamental truths about reality have historically required the deepest revisions in our intuitions. Atoms, evolution, quantum mechanics, relativity, each of these forced us to abandon deeply held intuitions about how the world works. Each of them made the world stranger and more wonderful. The answer to what came before the Big Bang, when it comes, will almost certainly be strange. It may require us to abandon our intuitions about the nature of time, about the nature of space, about what it means for something to exist. It may be stranger than anything we can currently imagine, but we will understand it. Not all of us, not immediately. But physics has, again and again, produced understanding of things that seemed beyond understanding. The interior of stars, the structure of atoms, the expansion of the universe, the merger of black holes a billion light-years away, whose ripples we felt in a detector on Earth. These were once as mysterious as the question we've been asking tonight, and they are mysteries no longer. The silence before the Big Bang is not eternal. It is a challenge, and challenges have, in the history of physics, a way of eventually meeting their match. Sleep well tonight knowing that the universe still has secrets at its very beginning. That the most fundamental question about our existence, where did all of this come from, remains wide open. That somewhere in a university office or a late-night conversation between physicists, the answer might be forming, taking shape out of the mathematics, preparing itself to be understood. The silence before the Big Bang is not empty. It is full of physics we haven't discovered yet, and the discovery, when it comes, will change everything. Good night.